Okay, so you can keep using integration by parts to define this function. You can keep integration by part or doing integration by parts to define the n derivative of this function. You can keep doing it. Okay, and define what it should be. And that is how you should define what the distribution should be. No, I don't think you can approximate as a series. Some mathematicians do, some physicists do. Okay, but you have to know what you're doing. Yes?
Why the first term is 0?
The first term is 0 because the other function is 0 outside its domain. It's only non-zero. And t is equal to 0. It's 0 everywhere else. So if you evaluate at 2 endpoints, this function is 0. So it forces this product to be 0.
Oh.
Okay? You can think of the delta function as a limiting case of this function. This is what you get in the lab. This is what you get in your course. Okay? So let's do example 9.19. 9.19. Okay, actually it tells you a new way to find the Fourier transform of a rect function. If you find that interesting, we can do that. Essentially, it tells you that we have previously shown that the Fourier transform of a rect function is sine sinc of omega. I think we have previously shown that omega over 2. Okay, it's shown in different parts of this course that this is true. And example 9.19 just gives you another derivation of this identity or this Fourier transform. So maybe I do example 920 first. If I have time, I'll come back to do example 919, which is this example. Okay, you can read it up yourself. Okay, let me do example 920 since I'm running out of time. Okay. So in this example, you're given the fact that the frequency response of the transfer function is given by this quantity over here. So you're asked to find what the output is if the input f of t is a rect function. Okay? You're asked to find the output y of t. Y of t is of course equal to f of t convolving with h of t. And you want to Fourier transform this back to h of t. Okay. How do I find the Fourier transform of that quantity that I have over there? Table lookup. What happens if it's not in your table? Give up. Right? So you have to be resourceful, a little bit resourceful when it's not in your table lookup. You try to write that in terms of functions that you have in your table lookup. Okay? So I can write h of omega being equal to 1 plus 1 plus j omega. Is this right? Let me check. 1 minus 1, right? So if you have that, if you bring under the common denominator, the first term becomes that minus 1. You get back that, right? So I can write this as a sum of two terms. And both of the terms, each of them, are in your table lookup. So what does the first term Fourier transform to? The delta function, very good. You Fourier transform to a delta function. So the second term, Fourier transform to what? Very good. U of t e to the minus t, and we just did that not too long ago. So h of t is found in closed form. Okay? Then the next thing you do is to go through this exercise of doing this convolution. And it's not a very difficult exercise. Okay? So you will have y of t being equal to rect of t convolving with h of t, which is written as delta t minus u of t e to the minus t. Okay? You just have that. And then the first term, rect of t convolving with delta of t, that we can do it blindfolded. Okay, what do you get? Or even doing it sleeping, maybe Guan Nan Gao. Guan Nan, you're not sleeping, are you? Guan Nan Go, right? Okay, what do you get for the first term? Rect T, okay, good. The second term you did before, right? Just remember? You knew how to do this. So I won't go through the second exercise because I think we did a very similar example like that before. You write the rect of t as two step functions, two unit step functions, convolve them, and then you do the second part. Okay? So, I'll just tell you the answer. So the answer looks something like this. Okay, it has exponential parts coming from here, and then you're subtracting two functions, and over here you can write something like qt plus half, qt minus half, kind of thing. Okay, you can write this convolution as we did before, something like that, and you have three terms interplaying with each other. Then if you plot them, then you get a function that looks something like that. Okay. So maybe we have 5 minutes left. We can do this one, unless you have other questions that you'd like to ask. Yes?
I'm still confused about delta t times t. When you use, I get it now.
You got it?
Yeah, I get it.
Okay, good, good. Good. Very good. You're enlightened now. So maybe you can use the last 5 minutes to build this, an alternative way of proving this identity. Okay? So we have delta t Fourier transforming to what? What does delta t Fourier transform to? Okay? Then you have this Fourier transform to what?
E to the negative j over t.
You have that Fourier transform to that. Then you can write the derivative. Just a way of deriving that identity is that you can think of a rect function. A rect function is just equal to that. It's 1, and then it's going to 0 at plus half and minus half. If you were to differentiate the rect function, what do you get? If you differentiate the rect function, you get two delta functions. Very good. Okay? Because on the rising edge, you get a delta function, and the falling edge, you get a negative delta function. And where are they located?
Negative 1/2 and positive 1/2.
Delta, one is located over here, so it must be over there. The other one is located over here. It must be t minus half. Okay, so you get that as your thing. And now if you, just a way of deriving this thing, if you take the Fourier transform of this, what does the Fourier transform to? You just, the Fourier transform of these two terms, right? So what does this Fourier transform to? Using that line above, direct substitution, what would you get? Robert, what do you get? If Fourier transform these two terms. What do you get when you Fourier transform the first one if you apply this formula? Anybody?
E to the negative j omega over 2.
I think it's just j omega plus 2.
P
Because you're
P
plugging
naught is
negative 1/2.
negative, so it should be this, right? These two terms of Fourier transform to that, right? Okay?
Multiplied by j omega.
What is that?
That's dy dt of vector t. So right hand side should be multiplied by j omega, right?
No. This thing equals that thing. That thing Fourier transform to that thing. Okay? Then this is equal to 2j sine of omega over 2. Right? But then using the derivative properties of Fourier transform, if the derivative of function Fourier transform to that, okay, what does a function itself Fourier transform to? Okay, a derivative is replaced by what in the Fourier space? J omega. So it must be this thing divided by j omega, right? So the j cancels. So you have 2 sine of omega over 2 divided by omega. And this can be written, this 2 can be put down here. So this is sinc of omega over 2, which is what you have over here. Okay, just another way of deriving this identity. Are there any questions regarding this? If no question, I'll let you go. I think the next section is also pretty long, 9.3.